Good morning. I am Dr. Deepa Philip. I am from IIT Kanpur, and today we are going to discuss in detail into the systems engineering process. So, we will do a complete overview of what the systems engineering process is about. The learning objectives for today includes understanding what the inputs to the SEP. SEP stands for Systems Engineering Process. So, in this lecture, whenever you see SEP, we are talking about systems engineering process. When we talk about SE, it is systems engineering. So, we will discuss in details about requirement analysis, functional analysis, design synthesis and outputs from SEP, systems engineering process again. So, quick recap of what we know already about what systems engineering process is. We seen this briefly in earlier lectures as SEP as a comprehensive, iterative and a recursive problem solving process. Comprehensive means it is all encompassing, it looks at the problem in a comprehensive manner. Iterative, we already studied what iteration is and recursion is. And if you remember in yesterday's lecture, we had discussed about it. Iteration is about the same function being applied to the same process is being applied to the function again and again to solve a problem that is identified. Whereas recursion is you are basically applying the same function, but to the lower levels of the product. So, you are keep on drilling down further or drilling upwards to realize something, to address an issue. So, it is a problem solving process, it is iterative and recursive. We already saw this definitions yesterday. And we also studied that it is applied sequentially one level at a time. So, as we said earlier, systems engineering to a large extent starts with what we call as the customer requirements at one level. Then from there you go down to the next level, from where you will identify the functional requirements. Then from there you will do the modules. From modules you will do the subsystems. Like this you will keep on drilling down. But if you are applying systems engineering to the customer requirements, you apply to the customer requirements throughout. Once it is done, it will give you the output to the next level, which is the functional requirements, and then you apply systems engineering process here. So, here is one application of SEP. Once it is done, you derive this, then you apply SEP again, you derive the next one. So, it is applied sequentially one level at a time. You move from one level to the next level, you do not apply randomly, and it is a top down fashion. As we discussed yesterday, the top down fashion is for basically converting the user requirements to a detailed documentation to the lowest level of product or a subproduct or a sub item that can be manufactured or produced or bought or reused. So, we bring it down to that level of smaller level of items. From there you integrate them back. So, it is a top down to get to this level of sub items, and then it is bottom up to get to assemble it back to the full product. We saw this yesterday. Then SEP schematic, we have seen this basic schematic of 3 circles integrating like this, and then we call this point as a systems engineering process. We had some requirement analysis, systems engineering, then life cycle. We had seen this diagram earlier also. We are going to look at it into it in a much better fashion. So, in detail, the systems engineering process, there is an input to the process, then there is a requirement analysis, which is the first step that we do, followed by a functional analysis, then a synthesis. We seen this diagram earlier, which has a system analysis and control, which is also what we call as the balancing act. And once you complete this, you actually get an output in which there is three loops: a requirements loop, a design loop and a verification loop. So, if we discuss here in a simple sense, systems engineering process SEP transforms needs and requirements into a set of system product system product and process descriptions, then you generate, along with that you generate information for decision makers, and also you do provide input for the next level of development. Okay. So, the systems engineering process transforms the needs and requirements. These are needs and requirements are specified by the user or the customer into a set of system, product and process descriptions. So, generate those descriptions. It also provides information for the decision makers, so that they can decide which alternative to choose from, and also provides input for the next level of development. So, from one level you move to the next one. So, in the requirement analysis, you can see that it analyzes the needs of the user, identify the functional requirements, and define and refine performance and design requirements. So, the needs and requirements needs to be translated into something called as a performance and design requirements. So, an example I will suggest to you is that if you talk to the defense people about developing an unmanned aerial vehicle, and if you, depending upon whom you talk to, they will have different needs. So, let us say for example, you are talking to various paramilitary organizations, then they will say that we need a UAV that need to be fit into the back of a jeep or a gypsy, or like a vehicle that they use for their transportation from place A to place B. The requirements is, it's a need, like we need the UAV to be transported. So, the need is transportable in the tailgate of jeep slash gypsy. Gypsy, I am talking about the Maruti Gypsy. Fair enough. Then how do you translate this into what you call as a performance and design requirements? So, the transportable UAV, that means it has to be, it means it has to be dismantleable. So, the need gets translated to a dismantleable plus quick assembly UAV is one example. The fit the tailgate of the jeep or a gypsy is like it defines the length of each individual part. So, we will say okay, each part cannot be longer than 1.1 meters, something like this. So, then this gives you the design requirements. The earlier part gives you the need requirements. So, you do the performance and design requirements based on the needs and the requirements specified by the customer. The customer might specify needs and requirements in a different fashion in very lucid terms, but the systems engineer is responsible for translating them into what we call as a exact numbers, which can be used by people for developing the system. So, once this is done, when we discuss these needs and other stuff, let us talk about in what forms the input comes from to the process. The inputs comes into the process in the form of multiple ways. It is, sometimes people say missions, sometimes like it has to fly day and night, it has to look at the surveillance, it should identify people, it should identify vehicles, it should identify big structures. All these kind of things the people actually, the customer do specify in this. There is MOEs. MOE stands for measures of effectiveness. So, sometimes people would say that it should be able to fly for 12 hours non-stop. So, then you see whether the endurance is available for 12 hours, which is another measure of effectiveness. Sometimes people will say constraint, that means it need to be silent. So, that means you cannot really use gasoline anymore because gasoline engines make noise. So, then you probably have to go for electric propulsion for the UAV to make it silent. So, sometimes customers specify constraints also, so that we do not want anybody to see it. And we do not want anybody to hear it. So, when these kind of loose stuff that statements you need to translate into design constraints, from which the final product specifications gets derived out, and you choose appropriate system to meet the need. Sometimes somebody might say that I want to do something, but there might not be the technology available to do it. A classic example of this is like somebody might say I want to go to Mars and come back in a day. Not possible, because probably the technology is not available at this point. So one thing the systems engineer should also be available about, known about, is what is the technology that is available presently, and can the needs of the customer be met by the available technological base within the country or within the organization or within the area. However you look at it, the question is obviously, is the technology base available? Then you might have done similar development earlier, and from which somebody comes up with some requirement, then you like, okay, we did this, or to some extent we did this in some project, and these are the issues we came up with. So we know if we go through this route, then you might end up with much more bigger problems. And so this prior development knowledge also comes into help while getting the process inputs from the customer. Also the decision requirements. So the customer says, okay, I want this. So when do we make the decision, or what are the parameters against with which we make the decision? That is also something that need to be specified out. So the customer says, oh, you make a unmanned aerial vehicle that fly for 12 hours and it can see both the day and night, and it is silent, and fine, that's a very loose statement. You make a unmanned aerial vehicle that meets the needs, and the customer comes back and say, well, this is kind of fine, but I want to see much more sharper images in the night. And then you will be like, then you get into this ugly debate. So you, before the finalization comes in, you're like, okay, if you see the image in which you can identify it's a human being, can't identify who is that person, but there's a human being, male or a female, at least to some extent you can identify up to that much. If that is acceptable, then we consider this project as successful. So that type of decision requirements are also specified as part of this exercise, or in the time of eliciting the customer inputs. And sometimes you will be forced to apply specifications and standards, like sometimes the customer says, okay, I want to paint it with this particular paint, and you are like, it's not allowed in the country because it is a lead based paint, and that's against the standards that's established by the environmental standards established by the country. So hence, let's do something else. So that could be possible, or we want to make a paint like this and want to do it, or we know how to make this paint, we will make it happen, and it will be painted by this particular paint. So in this is the first step in which the systems engineer talks to the customer, gets the customer needs in different forms. In this conversation, you use all these knowledges, know-hows and other things to come to a reasonable level of document which the customer and the systems engineer is capable of agreeing to, and say, okay, fine, this sounds like a reasonably good product to develop. Then from there, the needs are analyzed. That's where the requirement analysis comes into picture. And from there, functional requirements are elicited out. So as I said earlier, one of the functional requirements that in the UAV, the paramilitary specified to us in one of the projects that we worked for, was that it should take off from paved and unpaved surfaces. So unpaved surfaces is quite broad. It can be a paddy, it can be a field in which you have wheat or paddy being growing. It could be a river bed, it could be a rocky terrain. So we were like, can we be more clear? So paved means it could be any runway, public road, it's a straight stretch from where you have sufficient length for the aircraft to run up and take off, and there's a clear stuff above the road. And unpaved, what they said was, okay, place where there is no asphalt or blacktop, but it is flat and rolled and hard surface. Once that was specified out, then you could come up with, okay, fine, this is what the landing gear should do, this much big tires we require, all those other aspects were taken care of from that things. So that functional requirement of taking off from paved and unpaved surface gets translated to the type of wheels that need to be used in the UAV, type of landing gear that need to be chosen, the ground clearance that need to be put, and all those other aspects, and the damping on the suspensions. All those things has to be decided as part of that. Once this is done, the other aspect that also came out of the UAV was like the takeoff should be very short, should be within 100 meters. So now that translates to some power requirements of the engine. So how much power the engine should be able to give at full RPM, and what should be the weight. So the power to weight ratio was one of the things that need to be specified out of this particular customer need of 100 meters of takeoff. Then once this requirement analysis is completed, you move to the next level, which is called as a functional analysis. As I said earlier, you decompose it into a lower level. So usually the customer specifies higher level functions. The customer will say land on a paved and unpaved runway. He or she will never say this should be the thickness of the landing gear, this is the particular wheel that you need to be used, this is how much the capabilities of the shock absorber of the landing gear should be. That specifications is never given by the customer. It is something that is generated by the systems engineer for the product, the person who designs the product. So the higher level functions are usually specified by which we call as HL functions, which are defined by the customer. It needs to be drilled down into a lower level functions. You decompose them into much lower level functions. And once you decompose them into the lower level function, you have to ensure that these lower level functions are meeting the need or the functionality. The functionality is not lost in this process. So that is where this requirement loops comes into picture. When you start decomposing, you keep on rechecking with the needs. By decomposing this into such a lower level function, are we going to lose any needs out of this? And if the answer is no, then you go ahead and do it. That is the idea. Then you allocate performance and limiting requirements to all levels. The more levels, the lower levels you keep on going, you allocate performance and limiting requirements. You say this is what it is supposed to do, and it is not supposed to exceed this, or it's not supposed to perform below this. So those kind of limiting requirements, upper and lower limits, are established to each level as you drill down. And sometimes you might come across 3 or 4 subsystems for a simple small system, and they all need to be integrated. So each subsystem will interface with the other subsystem. So you have to define the interfaces, and you also have to refine those interfaces. How would those interfaces will work in unison to deliver the required function. And you also need to sometimes define and refine the architecture. Like when we were doing the unmanned aerial vehicle, one of the smaller versions, one of the major requirements that came out of it was to ensure that it fits in the back of a Jeep or a Gypsy, as I mentioned earlier. So earlier, first we started with designing something up to 1.5 meters in each individual length. Then pretty soon found out that 1.5 meters is not good, because after loading the UAV into the tailgate of a vehicle, you don't have any space. So to allow for people also to sit along with it, you have to further reduce the size. So each size, each individual part, the maximum length of each individual part was upper limited to 1.1 meters to provide additional space also. So this is where you have to refine the architecture. So the product design remained the same, but it was cut down into much more smaller parts for easy for assembly. It did increase the assembly time, obviously, because there are more parts involved. But yes, it was a compromise that was to be made, and the customer agreed to it. So all these things, when you are doing the functional analysis and you are looking at the needs, you require the input from the customer and go from there. So this requirement loop is an iterative process that makes it happen. Then once you have the functional analysis done, from there you actually go into what you call as a synthesis, or in another way to think about this synthesis is the design synthesis. Okay, you are synthesizing the design. So here you are transforming the functional aspects or the functional requirements that came up from the functional analysis to what you call as a physical system. Physical system or a physical product or a sub-assembly. So this physical thing can be a product or a subsystem or assembly, anything like that. Okay. So you identify the physical thing that will actually satisfy the functional requirement. That is part of this analysis. Sometimes you might want to say, okay, if this doesn't work, then what is the other option? Alternatives. You have to define alternatives. So the customer might say that, okay, we want a UAV that is silent. So, okay, fine. Let's go with the electric propulsion. Now, what type of electric propulsion? DC, AC, brushless DC, or high torque motor. There are quite a lot of options that is available. So we decided, okay, fine, we will go with the brushless DC motors of this particular caliber as the first choice. But as a backup, we will go with this one and this one power ratings. And if this doesn't work, then we will go with the third type of a motor. So we had alternatives. And you need to have them because sometimes the physical product might not deliver the thing that you expect. So you need to have an alternative at that time. You don't have time to look for alternatives at that time point. You already have to plan for that. Once these alternatives are there and once you start building the product, when you're synthesizing the design, pretty soon you zero in on certain things. Okay, this seems like a doable thing. Your past experience and other things comes into picture. So the preferred product and process solutions gets chosen out, or it kind of emerges out of what is being defined with what out of the synthesized design. Once it emerges out, then what you do is you also define the physical interfaces. So you would probably say that the autopilot or the control, the UAV, the autopilot should interface with the electric motor in which the input is how fast the motor should spin. So the autopilot is a digital system which would actually give a input to the motor controller, and the motor controller will determine how to change the speed RPM of the motor. So those interfaces, the interface between the autopilot to the motor controller and the motor controller to the motor, all those things need to be talked through and defined through. And once that is done, the other part that we also need to look at is what you call as, let me erase this point because it's kind of not clear. So the system analysis and control, we called this earlier presentations as balancing. This is the balancing or the controlling aspect of the whole system. You can keep on doing this requirement analysis, function analysis, because you need to some point of time get out of these loops and move forward. So the system analysis and controls allows you to do that. There's a bunch of tools that are used by systems analysis and controls or the balancing people that involves trade-off studies. You decide what trade-off, which one to be picked. You might compromise on something. You can't have everything. So what to be compromised on, that need to be done. Effectiveness analysis, which is like which one do you choose and how effective that it is, that also need to be analyzed out. Configuration management, interface management, data management, performance measurements, all these aspects that you see here, these are the tools that are used by the system analysis and control team or the people to balance the product or the system development endeavor, to ensure that the development process moves forward beyond the loops and you actually do get a process output out of it. And the process outputs are they're dependent upon each individual levels. As I told you, it's a systems engineering is applied to each individual level and you move in a hierarchical fashion, top down from one level to another. So depending upon which level you have, your process output might be different. It could be a decision database at certain levels, it could be the architecture of the product, it could be the set of specs which could be used to specify this is a product and you can decide it on to for the trade shows and other stuff. And it could also be thought about it as a baseline or like, okay, this is the baseline of the product beyond which we will not be willing to compromise, because then you will not be able to satisfy the customer needs. So once we have seen an overview of this. In the meantime, one loop that we have not spent too much time on is this verification loop. The reason for this is because we thought it's going to come much later down the whole lecture. But when you do the design synthesis, a lot of the time when you define and refine physical interfaces or when you choose a physical product, you need to verify that the choice meets the needs, because all the time you have to ensure that you are fulfilling the functional requirements. So this loop ensures fulfilling functional requirements by physical products. Yeah, the choices you make, some of them you might manufacture, some of them you will buy, but this loop is also necessary to ensure that the physical products that are chosen meets the customer needs or the customer functional requirements that are identified in the requirement analysis. So moving on, we'll little bit discuss more in detail about the systems engineering process inputs. As I said earlier, the inputs can include a wide variety of things, and some of them includes missions, it could be measures of effectiveness, it could be environments in operations. Environments. This could be operational environment, this could be some other environmental criteria. For example, if when the UAV development happened, the customer came back and said you should be able to operate it in high altitude area. Well, high altitude area is a very loose statement, but that's an operational environment requirement. So you need to now define what is a high altitude area, what height above mean sea level. So in this case, then finally we ended up deciding X feet above MSL, it should be able to take off. So that was decided by the discussions with the customer. So the operating environments do sometimes translate into certain performance requirements of the product. It could also be on the available technology base. I already mentioned that available technology base. Excuse me. It can also be into the decision requirements, because sometimes one of the decision requirements that was mentioned was the field commander should be able to look into the image that is fed or the video feed that comes back from the UAV and decide whether the target is hostile or not. Well, that's a decision requirement, the decision requirement for a person who is using the product. Now that directly translates to resolution of the payload or the camera that is on board of the UAV. So this is how you derive things out of it. And also sometimes you might also come across stuff like that. You might say that okay, requirements from other systems engineering exercises. One of the things that we have learned from other exercises in this similar UAV field was that the number of hours after which the engine need to be overhauled. So we had that number with us earlier. So we said, okay, this is what a frequency of overhaul if we use this particular engine, because we have already used it in some other product. Are you okay with that, or do we need to go for some other stuff? And when the customer said yes, we think we are fine with that number, then that actually helped us to decide the power plant, which power plant to actually go with that engine. I told you about the decision requirements already, and there is something else also called which is part of this. Okay, sometimes you also would understand the fact that the prior knowledge of systems engineering, it results in three. The prior knowledge actually requires, which we also call as corporate knowledge, results in three things. I would call these knowledges are one thing called as a tacit knowledge, the second one is called as tribal knowledge, and third one is what I call as corporate knowledge. Corporate knowledge. If I can't spell, you have to put the right spelling. Okay. So the tacit knowledge is it is defined as someone learned about something, but it is not shared or documented. So the knowledge that is learned by someone about something, but it is not shared or documented. It is not at all shared or documented. So tacit is usually with individual person. So if you go to a factory and you see a machine and you talk to the guy who is operating the machine, he will obviously have quite a lot of tacit knowledge, because he has been operating this machine on a daily basis, and he understands what are some of the things that need to be done and how can the performance of the machine be better. That's part of that is usually called tacit knowledge, but it is never written anywhere in the manual or any stuff, and sometimes the supervisor might not even know about it. So that type of a knowledge is called a tacit knowledge. The tribal knowledge, on the other hand, it's also an undocumented knowledge for sure. It's an undocumented knowledge that someone has learned but is shared with a small group. Let us call it a small trusted group, okay, or like a tribe. Okay. So, this is called the tribal knowledge. There is no documentation to this knowledge. It has been there, somebody learned about it, but the person has shared, it is shared with a small trusted group of people like a tribe or a group or a clique. They know about it. That is usually true because if there is a machining, there is a people who are working in a manufacturing cell, the people in the cell, there may be 4 or 5 workers there, they would have knowledge about each and every machine, so you can call those 4 or 5 people as a tribe, and they know what to do and what not to do. So then corporate knowledge is pretty much tacit plus tribal, and this knowledge is it's a combination of both, okay. And systems engineer need to be good at understanding or getting to this corporate knowledge. He should know about tacit and tribal knowledge that is happening in the organization or across the area where the product or system is supposed to be developed, because once you have that, you could actually do quite a lot more things, and you can actually develop a product which actually would meet or exceed the customer requirements. Instead of these requirements, I am kind of going to use the word dream. The customer might have dreamt about something, and you might be able to exceed that dream, which would be actually the management fads so actually call this as the wow factor. Okay. So the inputs, as you know, as the famous statement called GIGO, garbage in, garbage out. So the systems engineer need to be ensure that the GIGO does not happen in this process. Use whatever information is available, whatever the customer specifies, all those things need to be taken into consideration, even including the tacit and tribal knowledge and including the corporate knowledge, whatever you can, and come up with a really good requirements document from where a good system development can translate. This is probably the first and foremost, the most important activity a systems engineer would actually do. Then we move into the next one, what we call as the requirement analysis, and it is in a simple way, the requirement analysis, its aim is to develop the functional and the performance requirements. So once you have specified, the customer has given you the needs and the requirements, so then your first job is to analyze these inputs, which are the customer needs and requirements, as we saw earlier. Once you analyze that, from there you develop functional and performance requirements. Functional requirements means you are capable of doing something. Can you decipher a person in the night? That is a functional requirement. If you are using a UAV and you have a camera on it and it can decipher a human being from an altitude of 2000 feet standing in the ground, that is a functional requirement. The performance requirement would be the resolution. You can basically, like, how many times you can do it. Can you do it in all the weather, or do you require a clear sky? Can you see through these clouds? That would also be part of the performance requirements. So both functional and performance requirements together define the system. And the requirements, most important things are the characteristics of whether it is functional or performance. The requirement should be, they should be understandable. Understandable means people should be able to read it and understand, okay, this is what is being meant. Unambiguous, there should not be any confusion. Are we talking about, so somebody might say that we want a camera that can see in the night. And if you leave it that way, then obviously the ambiguity is that are you using a illumination source? If you say that we need to have a camera that would sense the heat in the night and using that thermal imaging happens, then people, okay, fine, we are talking about infrared cameras. So it should be unambiguous. There should not be no confusion about what you are trying to achieve. It should also be comprehensive because all aspects, everything that need to be considered for the product development should be considered as part of this. Also, like what we call as comprehensive review, every aspects, every possible aspects should be considered in this. It should be complete because once it is done, none of the needs and requirements should be left out. Completeness means accommodate or address every need and requirement. If you can't, then you should get approval from the customer saying that this cannot be met. Okay, let's remove this. Okay. So if not, customer approval is sought. If you can't fulfill it, then only the customer says, okay, fine, I don't want it. Okay, I'm okay with to compromise on that. This also is part of the process. And concise. It should be in such a way that people would read it and understand. People should not come to a level where say that, okay, fine, it is there, but I am not going to read this because it's such a huge document. So it should be concise. It should be in such a, it should be enough for somebody to read it and understand and then say, okay, fine, I can read this document. Also, please understand the fact that when you define the functional requirements, it also to some extent the design constraints also need to be specified. Sometimes there might be certain aspects that will constrain your the product that you are going to design, like the availability of the manufacturing process, sometimes might say, okay, this is the max I could do. Then those constraints need also be specified as part of the requirement analysis. And the functional requirements, if you want to spell out what are those functional requirements, or if you want to look into detail of what are the functional requirements, some of them is quantity. Quantity is how much, quality is how good, coverage is how far, you can think about it that way, timelines, that is a schedule, or the question is when, and availability, how quickly, and how frequently, that is also fine. Okay. All these questions, these functional requirements, once you answer these things or once you address these aspects of the functional requirement, you will come across, you will have a good functional requirement set up for a particular product or a system. The design constraints are typically derived out of environmental conditions, threats. Threats can be both internal and external. The environmental conditions, as I said earlier, can be the operating environments. It could be policies, many things like this. Okay, threats can be internal and external because there is, like for example, when we were developing the Tejas aircraft, one of the problem we faced was not being able to develop the engine, and the import restrictions on certain engines did delay the process. I would recommend you guys to read that story of how the non-availability of a certain engine delayed the indigenous development of the Tejas aircraft, which is kind of like to an extent a threat. It's an external threat to an extent. Contracts, how to define, make the contracts, is sufficient people available to make the contract, what should be written in the contract, what should not be written in the contract, that's all there. And then also there is called as regulatory standards, like what all regulations, like for example, when you do a unmanned aerial vehicle UAV design, then you need to look into what is the in India it is a DGCA or FAA regulation standards, what are they, and then you go follow that and agree that and design a system in such a way that you fulfill those standards as well, so that when somebody is going to take the UAV and fly it at some place, the regulatory agency does not come back and say not acceptable, or this doesn't meet the standards and you cannot fly. So I hope you guys understand the requirement analysis to a complete extent. Once it is done, the second one is the functional analysis, as I said earlier, and the user specifies what we call as HL functions or high level functions. And it's a job in the functional analysis is to decompose these high level functions into what we call as a low level functions or LL functions. And the only criteria is each function should be traceable to a particular requirement. Whose requirement? The user requirement. The requirement is that of the user. So the user requirements should be, so each function that you put, the low level functions that you derive from the high level functions, each function should be traceable to a requirement. You, in a way, we are saying that we are adding this function to ensure that the user, you are adding this low level function to ensure that the higher level function specified by the user is fulfilled. So that is a part of this. Also, you need to allocate performance requirements. So once you allocate the function, how would you measure that the function is fulfilled? So that requires performance requirement to high level and low level functions. So as you drill down the level from high level to low level, each level, low level functions, you will keep on adding performance requirements, and as well as restrictions also, that it cannot go upper and lower limits. So the performance requirements also involve specifying limits, low and high. So at the once you go through all these things, when you do the breaking down of the functions and allocate the performance requirements to the functions, what is the result? What do you get out of it? The end result. The end result is a product and an item description. You will finally bring down it to a product or an item descriptions in terms of the required performance. So this product or an item, that is something that you can be manufactured or made, or it can be bought or purchased, or it could be reused. So you bring it down to the lowest level of the product or an item description, which will satisfy the performance requirements associated with the function. This is called as the functional architecture of the system. The major tools used in functional architecture, which we will see in the later stages of this course, is the functional flow block diagram, which we call as FFBD. So the how the flow block diagrams are used to do the functional architecture. TLA is the timeline analysis, and RAS is the requirement allocation sheet. So these are the major tools that are used by the people who are in the functional analysis to come up with the functional architecture of the product or a system. Then we talk about the third major aspect of the diagram, the design synthesis. Where we do is you define in terms of physical and software elements that together make the product. Here you are basically specifying what are the physical and the software elements, what parts actually do make. So here you are like, if you are saying that I am going to use this particular sensor, then you would say, if you are buying the sensor, you will say the manufacturer, let's say for example, we will say Honeywell T3170 airspeed sensor, something like this. So you would define it in terms of the physical and you might require a software that will actually give the data to a data capturing device. So you specify all of this plus data acquisition system, something like this. Okay. So this together will make one part of the product. It doesn't have to be the whole product, a sub-product, sub-item, or a sub-assembly. So in this, we had a functional architecture earlier. The result of the design synthesis is we have the physical architecture. The physical architecture is defined as the basic structure that is necessary, that is needed for generating specs and the baselines. So you have the physical architecture of the product or the complete product of the system, product / system. During the design synthesis, we follow kind of two rules, which we don't try to violate this as much as possible. So each part should meet at least one functional requirement. This is the rule number one. So every part that you decide should meet at least one functional requirement. You should not add parts for the sake of adding the parts. It should be there to ensure that at least one functional requirement. This is the important word, at least. You can exceed more than one, but it should be there. It should not be there if it does not have any function in it. Rule number 2 is each part may support as many functions as possible. You can support more functions, or if you have multifunctional parts, then you might be able to reduce system size and assembly time. However, you might stand the risk of reliability. If the multifunctional part fails, then maybe multiple functions of the product might not work. So then this is where you do the trade-off. Okay, do I use this part, or do I provide redundancy to deal with it? And see, to deal. So maybe you provide 2 of those parts, so that if one fails, there is somebody else to take over. So this redundancy analysis also comes out as part of the this kind of a trade-off, multifunction parts and functional analysis, what we do. So in a way, this whole analysis helps us to understand or better understand. First one is what the system has to do. This is the first thing that we understand better. And then second thing that we do is what all ways it can do, the system can do what it has to do, how many ways or what all ways it can do what it has to do. And it also the we will also talk about the what are the priorities, or we understand the priorities of system, and what are the conflicts, what are the issues that we might have with the system. These many things are understood clearly by the time when we are done with the exercise, this complete exercise. Once the systems engineering process is over, you have clarity on these activities, and you have developed a physical architecture, you have a functional architecture. So you have gone down, drilled down from the highest level all the way down to the lowest level possible. So you started at the high level, you went to the lower level, and you have the product definitions, and you have the physical and the software elements defined out. Now you go back from here to realize the product. You start at the lower level and you reach the final product. We already seen that in the previous lecture, how do we go down, drill down and drill up. So this drilling down and drilling up is also why we call it as recursive approach. Okay, that is also there. We already seen that in the previous lectures. So the one part that we did not really spend too much of time on is the systems analysis and control, or what we call as the balancing bubble in the diagram. Okay, the balancing group. So what is the job of the balancing stuff? It is actually the technical management, or in a way in the previous diagram, the modified systems engineering, you might have seen this 3 stuff where we had a technical management group here with subgroups underneath this, and we drew diagrams like this. Well, this is more what the systems analysis and control. This is the equivalent of that SAC in the modern in both cases is systems analysis and control. It's the technical management activities. You are managing the technology in this case, and the aim of this is to measure the progress. So how good are we, or how much we have, how much progress we are making. So this is kind of something related to the project management. Evaluate and choose alternatives. The design document might have specified many alternatives. You might have to decide which alternative to choose, and you have to evaluate each alternative and then come up with a choice, which is a decision making process. You have to document data and you have to document decisions. So you have to document why you choose a particular alternative. You have to document what was the data to make that choice. So this needs to be documented as well. So the system analysis and control, SAC, ensures it does all these, it ensures these aspects while you are doing these 3 loop things. You are doing a requirement analysis, then you have a functional analysis, then you have a design synthesis, uh, and you go through these loops. But the balancing as SAC ensures that all these things are kept under control by, so come up with alternative decisions, the solutions to alternative decisions. So what are the solutions that you are, how did you choose the alternative decisions, technology decisions, okay, at what particular point you have there is a debate on which technology to be used, and then a decision need to be made. Then SSE ensures that appropriate technical decisions is end up being made. It also says, okay, what is the spec requirement? Somebody says, okay, this is what the spec is. Somebody says, this is what the spec is. And if then the SAC ensures that finally a spec, appropriate spec is chosen which will fulfill the need of customer or the functional requirement of the customer. And traceability, that whatever is being done, it is traceable, that there is a rhyme and a reason for why it was done, that's done. Schedules, which is the as we said earlier, time plus resource plus process. Okay. So that aspect is specified. How are you going to develop the schedule in which the system will be developed. You also, there will be multiple disciplines involved in what we talked about it as life cycle teams, the multidisciplinary teams. Okay. How thus those disciplines, different disciplines will be integrated together, that is also ensured by SAC. And the impacts of the customer requirements on the system development, that is always kept in check with the SAC to ensure that, okay, if what happen if we, this also is a trade-off. If one of the requirements is traded off against another, what is the impact on the product? And the SAC ensures that the customer is also kept in loop with that aspect. I hope with all these things we have a much more better clarity on the systems engineering process, SEP as a whole, and we seen the different aspects of the SEP. So this whole thing is what we call as the SEP, systems engineering process, with the inputs and the outputs of it. The we will come into the next lecture, we will actually go through different functional tools and tools available for functional analysis, requirement analysis, how things are being done, certain flow charts, certain diagrams, and custom built systems engineering tools to really realize the development of a system. So thank you for listening and see you next time.